so shall we start? And I could share now my screen.
Yeah.
Just a second.
Henning, are you ready? Are you ready, Henning?
I'm actually ready, yes.
Okay. Hi, everybody. Welcome to our seminar. It's my pleasure to introduce the speaker of today, Professor Henning Krause from University of Bielefeld. And he will speak about stratification of integral representations for finite groups. Please.
Yeah, thank you very much. I'm very happy to be back in Isfahan, at least virtually. And it's great that you have now started this new seminar. It's an honor to be the first speaker. And as you can see here, I'm sharing my tablet and have prepared some slides, but it will be a hybrid meeting, meaning that I will later on write on my slides and continue really in time. So not everything is prepared at this stage. So I'm going to talk about, so maybe somebody should make sure that participants are muted.
Yeah.
Good. But you can interrupt me if you have any questions, of course, but mute yourself otherwise. Okay, so you see, I'm going to speak about the stratification of integral representations of finite groups. Yeah? And maybe some of you have heard me before or have heard other people talking about stratification. The new aspect here is probably that I'm going to talk about integral representations, meaning that I'm allowing basically any commutative Euclidean base ring, whereas usually the stratification is done over fields. Yeah? So this is sort of the classical approach to look at representations over fields. Yeah, what I'm going to present is actually joint work with some colleagues. Alireza, can you make sure that others are muted? Sorry. Because we are the co-host. So this is joint work with Dave Benson and Shrikant Iyengar and Julia Pevtsova, as you can see. And it is sort of a long ongoing collaboration. And you see here a little picture from the Isle of Skye in Scotland. So the setup throughout the talk will be that I'm looking at a finite group G, and R is a commutative Gaussian ring. And my aim is, so what do I mean by stratification? The aim is to classify the thick and localizing tensor ideals of the category of R-linear representations. And I should tell you a little bit of the history. So this has been done already when the base ring R is a field. The pioneering work of Benson, Carlson, and Rickard from 1996 is mentioned here. Then they basically looked at the finite dimensional representations and the SIG subcategories. And then this was later extended, actually more than 10 years later, 15 years later, extended by Benson, Iyengar, and myself to classify the localizing subcategories for all representations, not just the finite dimensional ones. And one should really stress that the ideas go back to homotopy theorists like Mike Hopkins or Amnon Niemann, who did sort of similar classifications in the setting of commutative rings. So here's a plan for today. Well, I try, of course, to keep it not too technical. Yeah? So, but I want to give you some ideas, meaning to explain what is a stratification. Then I need to talk about the appropriate category of representations, because we are extending the base field, and this requires some sort of care. We are working sort of over an arbitrary commutative base ring, and then one has to define the right category of representations. And then I'm going to talk about a fiber-wise criterion, basically to reduce the classification problem to the existing classification over fields. And if one wants to use such a fiber-wise criterion, of course I will explain it, then one has also to look at the cohomology of fibers and basically compare them with the fibers of the cohomology. Yeah? So this is what I'm sort of doing at the end, and this is sort of the essential steps for this program. You know, these two steps here. Oops, what I'm doing. Oh, that's my fancy pen. Oops. So sorry. Yeah, so these are the two ingredients which one uses for this general stratification. Okay, so I give you sort of a short definition of stratification. I'm not assuming that you're familiar with all concepts, but nonetheless, I mean, I want to give you some idea. So what do I mean by stratification? This assumes that we are dealing with a tensor triangulated category. So T is a triangulated category which has a tensor product, symmetric monoidal structure, basically with identity. And our example is, of course, that we take the stable module category of a finite group, because we take the pass from the abelian category of representations to the stable category. We have a triangulated structure, and the tensor product is given by the tensor product over the base ring with the diagonal action of the group. So this is the example we are interested in, and it is actually a compactly generated and even rigidly compactly generated triangulated category, whatever that means. And the important ingredient for the stratification is that we have an action of a ring. You know? So we have a ring, and for example, here, when we look at the representations of finite groups, we can take the cohomology of the group with coefficients in R. So the ring S, which is acting, is a graded commutative machine ring, as for example here the cohomology ring of a finite group when R is a machine ring. Okay, and now we can look for any prime ideal in the spectrum of S. And by spectrum, I mean now the homogeneous or graded prime ideals. You know, for any prime, we can set up a local cohomology functor, sort of in analogy to what one does in commutative algebra or geometry. So there's a local cohomology functor, and then we can define for each object X, we can define its support just by taking the prime ideals P, so that the cohomology functor evaluated at X does not vanish. Yeah? So this is a very sort of simple, straightforward definition, given sort of that concept of a local cohomology function. Does that make sense? And the other definition or setting here, the other notation I'm using is that I denote by log with this tensor symbol the localizing tensor ideal generated by X. So localizing tensor ideal means it's a localizing subcategory, so closed under all coproducts and closed under tensoring with any. Yeah, so it's closed under coproducts. It's a triangulated subcategory, so closed under suspension and the cone or triangle forming triangles. And it is a tensor ideal, meaning that I can tensor with any other object and stay in that subcategory. So here's now the definition, sort of a short way of expressing what means stratified. So it is basically a way to classify localizing and thick tensor ideals. So T is stratified via this action of the ring S if whenever I have two objects, say X and Y, then the localizing tensor ideal generated by X is contained in the localizing tensor ideal generated by Y, if and only if the support has the same property. Support of X is contained in the support of Y. And if we look at the category of compact objects, so this is the notation for the category of compact objects, then we want that the SIG tensor ideal of X generated by X is contained in the SIG tensor ideal generated by Y, if and only if the supports have the same property. So this is a one way of defining what stratification means. And if one has this kind of stratification, then one sort of obtains a classification of thick and localizing tensor ideals in terms of subset of the prime ideal spectrum of S. So it's in that sense a classification. So the theorem I'm discussing today is here sort of joined with my collaborators when we take the stable module category of a finite group algebra, and I'm explaining what I really mean by this. Then this is actually stratified by the action of the cohomology ring. And as I said before, this is not entirely new. So there are predecessors to this from the 1990s, the celebrated result by Benson, Krause, and Rickard. And I'm giving you here the context. So it is for compact objects over a field. Benson, Iyengar, and myself did it for all objects, also over a field. And then there was this new development, which I'm basically presenting now, work by Eike Lau. He's an algebraic geometer, actually a colleague from Bielefeld. And he looked at this general case of an arbitrary commutative Noetherian base R, but assuming that the base is regular. And then he thinks of representations of a finite group basically as an affine scheme with a G action. And so in that way, he classifies sort of using this sort of geometric approach, the thick tensor ideals. I mean, he thinks of it as a delinear manifold stack, and he looks at the category of perfect complexes basically over that. And there's also related work by Tobias Bartel. There's actually a couple of papers, I think, on the archive. Here he classifies actually all objects. So he classifies the localizing tensor ideals. Again, under the assumption that the ring R is regular. And he thinks of this as representations of classifying spaces the classifying space of BG. So what I'm saying is that he uses sort of a homotopy theoretic approach, which is quite different. He uses also the sort of language of infinity categories. So there are sort of various approaches now on the market. And as I understand, there is actually also progress from these authors, Lau and Bartel. They are also able to remove the assumption here that the ring is regular. Yeah? So this seems to be now an established result, what I'm presenting here today. Okay, so let's look again at the plan. So I gave you the concept of stratification and formulated sort of the main theorem. And now I want to explain more about the appropriate categories. And I'm going to write here. So categories of representations. So what is the right setting? So R is a commutative ring, as you recall. Actually, I don't need to assume that the ring is Noetherian. The discussion is sort of in full generality. And A is a finite projective R algebra. So this means that A is finitely generated projective as an R module. Yeah, so it's an R algebra with that extra property. And then we look basically at the category of all modules, let's say right modules, but that's not really important. And inside, we want to look at the lattices. So lattices means category of A modules, the category of A modules which are projective over R, over the ring R. So these are also called lattices. And so this is the definition. And we also look at the category small mod A, R. These are basically the finitely generated lattices. So the category of A modules which are finitely generated projective over the ring R. So we have a special situation when we look at group algebras, namely group algebras are self-injective. And what does it mean here in this context? So the following conditions are equivalent. So we set the dualizing module is by definition the dual of A, but now the duality over R. So we hum into R, and then that duality moves sort of left to right modules and vice versa. So we call this the dualizing module. And then the following are equivalent, that the additive closure of this dualizing module, is the same as the additive closure of A, so coincides with the finitely generated projective modules. The fact is equivalent to that mod A, R is actually a Frobenius category. Sorry, I forgot to make a remark. Well, let's just move this a little bit down. So the remark I wanted to make, oops. So these categories of lattices and also the category of finitely generated lattices are actually exact categories. Are exact categories with enough projectives and injectives. Maybe it's actually not a remark, but rather a lemma one has to prove, but it's not so difficult. So we have exact categories with enough projectives and injectives, and if projectives and injectives coincide, then one calls it a Frobenius category. Yeah, and an equivalent condition is that all lattices form a Frobenius category. Yeah, and then one calls a self-injective. So then A is a self-injective R algebra. It's of course always relative to the base ring R. Okay, and the example to have in mind is group algebra. So the group algebra RG is self-injective. I mean, this can be generalized Hopf algebras, also self-injectives, but let's not worry about this. So now let A be self-injective. So let A be self-injective R algebra, should say, and we denote by proj the category of all projective A modules. So then we actually have inside of A modules the lattices, and now inside the category of lattices we define actually what we really want to study. So which I denote by mod A, R, the localizing subcategory. Localizing subcategory generated by the finitely generated lattices. So what do I mean by localizing subcategory? So this means localizing subcategory means closed under all coproducts and satisfies the 2 out of 3 property for short exact sequences. Yeah, so we have an exact structure. The category of lattices has an exact structure, and we look at now a localizing subcategory generated by the finitely generated lattices. And this is actually the category we are about to stratify, yeah? Because there is no reason why this category actually coincides with all lattices except when the base ring is regular. So we also want to look actually at complexes of projective A modules. And inside the homotopy category of complexes, so I denote this by K of proj A, the category of complexes up to homotopy. Inside, we look at the relative complexes. Basically, we want complexes. I mean, here we have for the lattices the extra condition that the lattices are projective over R. When we talk about complexes, the analog is being a K-projective complex over R. So we look at K-projective complexes, but this is not really good enough. So what we are really taking is the localizing subcategory generated by objects X with the property that X is a compact object, and well, I could say it's K-projective over R, but sort of more explicit, it is perfect over R, because then it's also a compact object. So compact and K-projective means it's a perfect complex, so a bounded complex of finitely generated projective R modules. Yeah, because we can always restrict a complex of A modules, view it as a complex of R modules, and then it should be a perfect complex. So that's a definition. And here's that remark I made already. When the ring R is regular, yeah, so for example, if we just take the ring of integers or any Dedekind domain, which is already interesting, then we have actually an equality. So then all the lattices coincide with this module category generated by the finitely generated lattices, and also the homotopy category of all complexes coincides with this relative category. Because basically it's an empty condition. The second condition, perfect over R, is then an empty condition. Okay. That was my discussion of the category of representations. Are there any questions at this stage? I cannot see everybody, so let's see. So how do we continue? So we have now, let's look again at the plan. We have talked about stratification. We have now defined the appropriate category of representations. And now I want to tell you a fiber-wise criterion. So basically reducing the problem of classification to the known case where we consider representations over a field of prime characteristic, basically. So let's do that. And this is actually fairly sort of straightforward. Wait, but look at my notes. There's still something I should talk. So my discussion of representations are not complete. I want actually formulate also some lemmas. So when A is a Frobenius category, then we can attach to it its stable category. So the stable category. And this is, of course, triangulated. It has a triangulated structure. Yeah, so the exact structure of the Frobenius category induces triangulated structure on the stable category. So here's the lemma. So the stable module category is compactly generated the compactly generated triangulated category with the compact objects. So this is a notation for the compact objects equivalent to the finite stable module category. Yeah, so I take the finitely generated lattices and take its stable module category. And the same for the category of complexes. This is also compactly generated, basically by definition. Compactly generated. But it is interesting to identify the compact objects. I mean, this is the content of the lemma. So if I look now at the compact objects, so this is basically the complexes of projective, finitely generated projective A modules. So small proj A complexes of finitely generated projective A modules bounded below and having only cohomology in finite, non-zero sort of vanishing of cohomology in finitely many degrees. But the cohomology really refers to the sort of given exact structure. Yeah, this is, so I'm referring to the exact structure which we have on the lattices. Anyway, so this is equivalent to the bounded derived category of this exact category. Yeah. So there is a sort of consequence of this proposition. So there is a recommand. Actually, we have the stable module category of representations, which is equivalent to the acyclic complexes of projectives. Then we have the inclusion into all complexes of projectives, always relative with respect to R. And then we have the corresponding quotient, which identifies actually with the derived category of mod A. And so there's a recommand, meaning that these functors have adjoints, the usual recommand. And this induces on compacts. So the left adjoints, the left adjoints functors from right to left, they preserve compactness. And this induces, therefore, a triangle on compacts. So when I restrict to compacts, a triangle equivalence between the bounded derived category modulo perfect complexes and the stable module category. So this is a singularity category if you want. Yeah? So we identify the singularity category here with the usual stable module category. I mean, all this is sort of somewhat classical when one is working over field, goes back to Ricard, Buchwald's, and so on. But here we need to be more careful because we allow an arbitrary, actually, we don't even assume Noetherianness, we allow an arbitrary commutative base ring. And then this is sort of the right setting. So another remark I have to make, because the stratification also refers to this tensor structure. So if A is now, say, commutative Hopf algebra or particular group algebra of a finite group, then the stable module category and also this homotopy category of complexes of projectives. By the way, I mean, because it's a Frobenius category, projectives and injective objects do coincide. Yeah, so you can also think of it as K-inj if you want, instead of K-proj. Yeah, so anyway, so the homotopy category of projectives or injectives relative to R have a tensor structure. Given by the tensor product over the base ring R with the diagonal G action. Yeah, that's the usual way to think of tensor product for group representations, and they are rigidly compactly generated with an action, with a canonical action given by the group cohomology. So S is by definition now the group cohomology. Remember, our notion of stratification was always relative to the action of some graded commutative ring, and in this case we take the cohomology. No, it's not a definition, it's rather an isomorphism So we take the trivial representation R and take its Ext or Yoneda Ext algebra. This is isomorphic to the group cohomology ring with coefficients in R. Okay, so this connects basically to our notion of stratification because there is a tensor product involved. And now I'm actually ready to move on to the fiber-wise criterion, which is actually fairly straightforward. Fiber-wise criterion. So again, A is the group algebra. Finite group. R is a commutative Nicene ring. And for any module, so I look now at representations which are lattices. We set the fiber at a prime P to be M tensored over R with a residue field. So P for any prime P in spec R, so prime ideal of R, and Kp is by definition the residue field. And this is actually a module over the algebra A, K, P. Yeah, so we take the fiber at the prime P, and this is now a finite dimensional self-injective algebra over that field. Yeah. So here's a theorem. So we can actually detect localizing ideals using these fibers. Yeah? So for two objects, X and Y, either in the stable module category of A, R, or in this homotopy category of complexes of projectives, we have that the localizing tensor ideal generated by X is contained in the localizing tensor ideal generated by Y, if and only if the same is true when we go past to the fiber. So if the localizing tensor ideal of X, Kp, is contained in the localizing tensor ideal generated by Y, Kp. Yeah? And of course, this is for all primes. Yeah? So I can detect on on the fibers, the localizing subcategories. And an obvious consequence, now we know we have a stratification. You remember my sort of brief history of the subject. We have actually a stratification when the ground ring is a field. Yeah? So in that way, we obtain a stratification here now. So the stable module category and also that homotopy category of complexes, projectives, are stratified via, well, I attach to any object X its support, but now I take as a support just the union over the supports of the fibers. Yeah, and run through all primes in spec R. So this is contained in the union of the spectra of these cohomology rings of G with coefficients in the residue field. Yeah, I mean, this is an immediate consequence. If I take that definition of support, basically taking the unions of the supports at the fibers, I have sort of a stratification. But this is not really what we want, because we want a stratification in terms of the group algebra of G with coefficients in R. Here I have now the coefficients, as you can see. Here we take the coefficients in these residue fields. Okay, so this is then my final discussion.
Sorry, Henning.
Yeah, sure.
It's this is the unit disjoint or here?
Yeah. I take just the disjoint union inside the sort of disjoint union of the spectra of the cohomology rings. Yeah.
Okay. So it's not clear how it's related to the spectrum of the cohomology.
This is exactly what I'm going to discuss now.
Okay, thank you.
Yes, yes. You're absolutely right. I mean, this is what is still missing. So this was my, this will be the final section, the cohomology of fibers versus the fibers of the cohomology, right? Okay, so remember S is our cohomology ring with coefficients in R, so the X algebra of the trivial representation. Yeah, and we want to stratify with respect to the action of this ring. Yeah, so this is a Nician ring, classical result. Evans, Svenkov, Rouleau. So let me denote by eta the ring R to S, basically identifying R with the degree 0 cohomology of S. And then we have actually a factorization. So let me also define S of P to be the cohomology at the fiber. Yeah, so for each prime in R, and this factors through S tensored with the residue field. And let me denote this map by kappa P. Yeah? So P is any prime in spec of R as before. And any ring homomorphism between commutative rings sort of induces a map on the spectra. From now, this goes from spec S to spec R, of course. Spec R. That's my notation. And here's a little lemma. So if we take the support of a fiber. So we take X, a module or complex, and take its fiber. And now we apply kappa B A, then this is the same as support of X intersected with eta, the pre-image of eta A of the prime ideal P. Yeah? So this is somehow how the support of the fibers relates to the support of the original complex or object or module. Yeah? This is sort of a nice feature. And then we have the following theorem, namely that the spec of S of P, yeah, so that was the cohomology ring of the fiber, identifies via this map KPA with the spectrum of S tensor KP inside, and we view it as a subset of spec of S. So this is a bijection. It's even a homomorphism, but it's good enough to know that it is a bijection. And then a corollary of that. So corollary, then the stable module category of the group algebra, and K Hodge complexes of modules over the group algebra are stratified via the group cohomology. Yeah, I mean, this is somehow an upgrade from the previous stratification. I mean, if you look here, as Charu sort of was pointing out, yeah, I mean, here we are looking at the spectra of the fiber, but we get actually at the end a classification or a stratification in terms of the spectrum of the original cohomology ring. Okay, so I think my time is basically over, and I thank you for your attention, and of course I'm happy to answer any questions. Thank you.
Thank you, Henning, for your nice talk. Are there any questions, comments?
Yeah, thank you. Can I ask? Can I continue my question? Here, I mean, the last theorem to somehow maybe I identify the disjoint union of that spectrum with spectrum S, or not that one. I mean, previously you have a disjoint union of spectrum of SP.
Yes.
But that disjoint union is only mapped to spectrum S, right? Not identified.
Well, I mean, no, it's not. I mean, it is sitting inside as a subset. I mean, this is the point, yeah. But it will not be disjoint, yeah. If you sort of go through various primes, I mean, then there is sort of an possible intersection.
I see. So eventually the support of S should mean a subset of spectrum S.
Yes, exactly.
I see.
Mhm.
I see. Okay. Okay.
Yeah. So my, I mean, my equality here is somewhat misleading. Yeah. So maybe one should call it sort of a support tilde. Yeah. The original support in a tensor triangulated category with an action of a ring R or S is our ring which is acting, is a subset of spec S. Yeah?
Yes.
And here I was somewhat sloppy. Yeah.
So then somehow you have to identify the some element, so then got the final support.
Yes. Mm-hmm. Yeah.
Yeah. Okay. Thank you. Thank you. Mm-hmm. I have another question. So in this picture, is the singularity, because you are not assuming R is regular. So is there some way that the singularity of R play a role or playing a role?
No, this is basically what one avoids by that definition. Yeah, it's a good point. I mean, this is exactly why I sort of discuss this category of representations. I mean, here, basically, we take only the modules which are projective over R. You know? So the singularities are basically ignored in a sense. You know? And the same happens here. So these objects here, they are all K-projective. Yeah? So one is basically working away from the singularities of R.
I see. I see.
I mean, if you take sort of singularities into account, then sort of that gets somewhat more complicated. Yeah? And all the, yeah, sort of features of the base ring will sort of interfere in some,
yes,
in some way. Mm-hmm.
Yeah, thank you.
Mm-hmm. I mean, the problem becomes somehow, I mean, you could also study sort of other categories of representations if you sort of allow an arbitrary base ring, in particular with singularities, but then it becomes somewhat wild, yeah, a wild problem. I mean, here, the category of representations is basically defined in such a way that the group cohomology is sort of stratifying, yeah. You can make other choices, other sort of reasonable choices of representations, but then it becomes more complicated. Yeah? And the group cohomology is not good enough.
Not enough.
Yeah.
Yes, yes.
Actually, there is a little note by sort of my co-authors, Dave Benson, Shrikant, and myself, where we explore also these sort of other possible categories of representations, but we also point out that it gets complicated in small examples. You see it already in very small examples, the complications.
Yeah, thank you. Yeah, I remember vaguely that previous paper. Yeah.
So any other question? So it seems there is no other questions. Let's thanks to Henning again. Thank you.
Well, thank you for having me visiting, and I wish you all good luck with your future seminars.
Thank you. Thank you.
Thank you.